Hello, and welcome to this recorded e-learning on basic FPGA architecture for the Virtex-6 device family. My name is Frank Nelson. I will be your instructor for this module. This module introduces SLICE and I/O resources available in Virtex-6 FPGAs. This basic FPGA architecture module limits its scope to discussing the SLICE and I/O resources. Please note that there are also corresponding memory resources and clocking resources recorded e-learning modules available as well. The objectives of this module are that you'll be able to describe the CLB and SLICE resources available in Virtex-6 FPGAs, that you'll be able to describe flip-flop functionality and its limitations, and be able to anticipate building proper HDL code for Virtex-6 FPGAs. All Xilinx FPGAs contain essentially the same basic logic resources. Slices, which are grouped into configurable logic blocks, or CLBs, contain combinatorial logic and register resources. As you can see from this picture, there are a lot of CLBs on this die, while each device family is offered with a different number of CLBs. Determining which density is right for your application often requires you to at least synthesize your design before choosing an appropriate density of FPGA. Only with some experience can you properly estimate how many SLICE resources will be necessary for your design without at least synthesizing the design first. The SLICE resources are the most essential and fundamental to an FPGA design. They include LUTs and registers. LUTs are built to create your combinatorial logic resources. Each has an associated register with it. The LUTs and registers are grouped into slices, which also have other dedicated resources. Besides LUTs and registers, slices also have carry logic resources, which are designed to implement arithmetic logic functions with high-speed performance due to the dedicated carry chain, which runs vertically in columns from one slice to the next. The implementation tools select an appropriate routing that may include different kinds of routing resources. The solution that is routed is designed to try and meet your timing needs. To do this, it is important that you add timing constraints with the ISE design suite so you can communicate your timing objectives to the implementation tools. This will allow the software to choose the most intelligent routing solution to meet your needs. In fact, the mapping and placement of logical resources is handled by PAR, the placement and routing utility. In Virtex-6, all routing, besides the carry logic resources, is routed through the switch matrices. While understanding the interconnect structure is seldom needed, this diagram is meant to describe the population between slices and CLBs. You see, in between each CLB is a switch matrix which is designed to connect to other switch matrices as well as the neighboring CLBs. The possible interconnects are called PIPs, or programmable interconnect points. Please note that proper use of global timing constraints, which are explained in the Essentials of FPGA Design course, are going to be required to communicate to the tools your timing needs. Now, combinatorial logic is stored in lookup tables or LUTs. Lookup tables are also sometimes called function generators. The capacity of a LUT is limited by the number of inputs, not by the complexity. So delay through the LUT is constant regardless of what logic function is being performed inside. Each Virtex-6 slice contains a 6-input LUT that can also be broken into two 5-input LUTs. This allows the resource to be broken down if necessary to assure maximum device utilization. Every customer must understand the input limiting nature of LUTs. Because many customers are used to building with ASICs, it is important to understand that the HDL code you write needs to be optimal. This is because ASICs are faster than FPGAs, and it's much easier to get good speed from an ASIC with suboptimal code. This is highlighted when you consider what you would get if your combinatorial logic had 7 inputs. Because the LUT has 6, your synthesis tool would be required to add a second LUT in series with the first. This would then dramatically increase the delay associated with this path and cut the maximum frequency possible. Also keep in mind that if you're trying to design at the maximum speed quoted in the device datasheet, you have to remember to limit all of your delay paths to one LUT or one logic level. This is not typical, but some customers do it by extensively using pipelining and by minimizing their combinatorial logic. The Designing for Performance course discusses pipelining. every customer that builds his or her first FPGA inevitably struggles to get optimum speed because they're not using optimum HDL code. I recommend you listen to our HDL coding style RELs so you can be as successful. Xilinx also provides the Xilinx Synthesis and Simulation Design Guide at support.xilinx.com for your reference. It includes terrific coding examples and detailed design recommendations. Each CLB contains 2 slices. From this diagram, you can see that each slice has 4 LUTs, 4 flip-flops, and 4 flip-flops that can also be programmed as latches. We added the additional registers because the LUTs can be broken into 5 input LUTs, and this should help designs get more logic out of the FPGA design. The carry chain is supported on 4 of the 8 flip-flops. There are also dedicated muxes, which can be used to build larger multiplexers and save LUTs so your system can get higher speed. In this diagram, we see a number of muxes used to connect the LUTs together. Each slice contains 2 F7 muxes that groups the outputs of 2 LUTs and can create an 8-to-1 multiplexer. Each slice also contains 1 F8 mux that combines the outputs of the F7 muxes and can thus make a 16-to-1 mux. The mux outputs can drive out of the slice or connect to the available flip-flop latch. These dedicated multiplexers are used to improve the speed of large multiplexers and save LUTs for other purposes. The reason that these multiplexers improve the speed of the design is because there is dedicated routing between the multiplexers that are low fan-out and fixed between the logic resources. It is also fast because the dedicated multiplexers are faster than building the equivalent logic just with LUTs. What is most important to remember is that each of the dedicated resources has an intended purpose of saving LUTs and improving the speed of your design. Also be aware that if you are going to code for a large multiplexer, you code with a case statement in your HDL. This is required for inference of the dedicated hardware mux. Carry logic is a dedicated hardware resource that improves the speed of arithmetic functions, such as adders, accumulators, subtractors, and comparators. From the diagram, you can see that the slices are grouped into one carry chain. Please note that carry logic will propagate the carry signal vertically upward. This is important to note because most designs use carry logic extensively, and by using it, the least significant bit should be placed at the bottom of the carry chain. Likewise, when carry logic is used, bit ordering should be followed by the designer, with the less significant bit being placed beneath the more significant bits. Each slice has 4 flip-flop latches and 4 flip-flops. The difference between them, besides their programmability as a latch, is that the flip-flop latches, seen here labeled FF/L, can be driven by the LUT, carry chain, or the wide muxes. Conversely, the flip-flop can only be driven by an 05 input, which can come from the 6-input LUT when it is used as 2 5-input LUTs, or from a separate input to the slice. These limitations are not as much of a big deal. In the end, if you're building lots of lower input functions that share inputs, as is required to have the 6-input LUT broken into 2 5-input LUTs, you should end up with the flip-flops being used quite a bit, and this will aid your pipelining and improve the speed of your design. All flip-flops and flip-flop latches share the same control signals. The group of associated control signals with the flip-flop is important since only flip-flops that share the same control signals can be grouped into the same slice. This means that if you don't manage the use of your control signals and try to reduce the number of control signals your design has, then you might have trouble getting high device utilization. The set and reset signal can be configured as synchronous or asynchronous. For synchronous design purposes, Xilinx recommends that unless absolutely necessary, your design should use a synchronous set or reset rather than an asynchronous one. We discuss good synchronous design practices in the Essentials of FPGA Design course. To help designers with this, we have made a series of Virtex-6 and Spartan-6 HDL coding style RELs. They discuss the impact of this and provide you with many good design practices that will help you get high performance and high device utilization. So check these out. Many, but not all LUTs in the FPGA can be configured for distributed RAM. This is a small 64-bit memory that can perform a single, dual, or quad port memory. Each port has independent address inputs and has a synchronous write and an asynchronous read. There are 4 configurations, as you can see from the slide. Most customers use these resources for DSP applications. Sometimes customers try to build larger memories out of these. It is possible, but the extra logic to connect these small distributed memories together make their performance prohibitive. So you may want to consider building a larger memory instead with using the dedicated block RAM resources. In general, those customers that build with this are using the core generator or the system generator to build their DSP application. Many LUTs can be configured as a 32-bit shift register as well. This is used primarily as a pipeline delay element for balancing pipelined applications, but it can also be used for variable length shift registers, synchronous FIFOs, CAMs, or for pattern generators. It is a cascadable resource that allows it to be cascaded to up to 128 bits in length. The most challenging thing with this is that most customers don't realize that it is not loadable, has no reset functionality, and only offers serial in, serial out capability. So if you try to infer it with any of these behaviors, your synthesis tool will instead infer regular flip-flops. And of course that will be a big waste if you're building a large component and expecting the shift register LUT to be used. The benefit of this resource is that it can effectively provide the work of 32 registers with a single lookup table. And in pipelined applications, that is a huge savings. This is an example of the use of a shift register LUT. The SRL can be used as a programmable delay element, or a no operation or no op. In this example, you see a 64-bit bus being processed through operation A, B, and C. A has a delay of 8 clock cycles, B has a delay of 12 clock cycles, and C has a delay of 3 clock cycles. Because the data processed is also grouped at its output with a multiplexer, these data paths must synchronize so that appropriate data is compared at the multiplexer. To do this, the SRL can be used to delay the C operation by 17 clock cycles. Now, if we were to do this with registers, that's the normal CLB registers, it would require over 1,088 registers. If we use the shift register LUT functionality instead, we only need 64 LUTs, each programmed for 17 clock cycles of delay. So this example uses 64 LUTs to replace over 1,000 flip-flops and the associated routing resources to complete this. Pretty good justification for using the SRL. Because there are so many registers in the FPGA, pipelining is an effective way of designing to increase design performance, because pipelines sometimes become unbalanced when too much logic must be generated. It is necessary to delay some of these signals to do just that. One of the best uses of the SRL is, just as we've seen here, is to add a delay element to balance a pipelined application. So now that we know that each LUT has 3 different configurations, logic, distributed RAM, and the shift register LUT, we can discuss the 2 types of slices in Virtex-6. There is the SLICEM, which is the full slice, and is about 25% of the available slices in your device. In this case, the LUT can be used for logic, memory, and the shift register LUT. It also has access to the wide multiplexers and the carry chain. The rest of the slices are Slice L, which are logic and arithmetic functionality only. So the LUT can only be used for logic. There's no distributed memory resource there. It also has wide multiplexers, and of course the carry chain is associated with it. Most customers don't use as many LUTs for distributed memory or even the shift register LUT as you might think. So this segmentation of functionality does not usually have a performance impact, but instead will save transistors for other purposes that will be more beneficial to the designer. Also keep in mind that the implementation tools will lay your design out onto the die, so understanding which slices are on M or on L is not important. All we wanted to do was explain that they are different and show you how they're different. The input-output blocks, or IOBs, interface between the FPGA and the outside world. IOBs are grouped into I/O banks, which are located in columns throughout the device. IOBs contain registers and some specialized resources, but the main purpose of the IOBs is to clock data into and out of the FPGA. In fact, using registers to clock data in and out of the device is the fastest way to move data, by running it through the IOB registers. Besides registers, the IOBs contain interface logic that is designed to translate the internal voltage domain of the FPGA to whatever I/O standard you're using. This saves you from having to add all the necessary interface logic outside the FPGA. Now, this requires that each bank share a common power supply for inputs called VREF and outputs called VCCO. These voltages vary by I/O standard, but Virtex-6 supports many I/O standards. Fortunately, many of these standards can share the same power supplies. Now, Virtex-6 has between 9 and 30 I/O banks, depending on the device density, and each I/O bank has 40 I/O pins associated with it. The Versatile Select I/O resource was first introduced with the Virtex family of FPGAs several years ago. It has been enhanced with every new product family ever since. I/O standards have been added and selected to support what our customers require. Virtex-6 FPGAs support over 40 I/O standards, including those you see listed here. But check your datasheet to see if your I/O standard is supported. Note that there are memory-specific standards of varied classes, differential standards that require 2 I/O pins to receive the signal. The differential signaling standards include LVDS and LVPECL. The signal-ended I/O standards include LVCMOS, SSTL, and HSTL. The Select I/O feature allows direct connection of the FPGA pin to external signals of varied voltages and thresholds. This optimizes the speed-noise trade-off and saves you from having to place interface components onto your board. All of the dedicated interface logic already exists and can be selected on a pin-by-pin basis. However, note that to mix different I/O standards into the same I/O bank, you must be aware of the I/O banking rules. These rules apply because each I/O bank shares power pins for each of the input and output pins in the bank. Specifically, the VREF powers the input circuitry, and the VCCIO pin powers the output circuitry. So whichever I/O standards you group into each I/O bank, make certain that the input pins can support the same VREF, and the output pins can support the same VCCIO. Now, as an FYI, this is easily planned by using the pin-ahead utility included with the ISC software. This slide is just trying to show you how differential pins work in Xilinx FPGAs. Each pin in the device can be configured as single-ended or differential. Now, you should keep in mind that every pin is predefined as part of a P or an N pair, or specifically a P or an N pin, as shown in this diagram. And for every pin, there's a corresponding pair that's pre-assigned. Note, pre-assigned. So if we were using a differential I/O standard, I'd have to plan to use my P and N pairs accordingly. And of course, these pairs would be pre-paired, shall we say, or prefixed. So I don't have complete flexibility to plan my design's pin layout, although I do have quite a bit of flexibility since any differential pair can be placed on any pair of differential pins. If a single I/O pin was configured as single-ended, then the corresponding P or N pair would be free to be a single I/O pin of a compatible I/O standard. And in this case, the diagram we see showing the interconnection between the two pins would not apply. Note that these limitations have an impact on your pin layout, so be sure to plan on laying out your differential transmitter pins properly and early by using the pin-ahead utility that's located in the plan-ahead software. The primary use of the IOBs is for registering data. In this slide, you see that there are 6 registers associated with the IOB to support the use of double data rate applications. As you can see, there are 2 registers for input, 2 for output, and 2 for 3-state enable. However, the IOB can still be used for single data rate applications just as easily. Each register supports separate clocks and clock enables for input and output, but the set and reset signals must be shared. To clock the DDR registers, remember that you can use any pair of the PLL outputs that are 180 degrees out of phase, such as clock 90 and clock 270 outputs, likewise the clock 2X and clock 2X phase shift by 180, or even the clock FX and the clock FX phase shift by 180. Besides the register and select I/O resources, there is also the SerDes functionality built into each IOB. This includes both parallel to serial and serial to parallel conversion. This is a programmable functionality that can decode a wide range of signals. The OSerDes/iSerDes combination is probably one of the most useful and radical developments. Many issues that you would traditionally address by using the FPGA fabric are handled within these blocks. Tasks such as training pattern recognition, clock-to-data alignment, and crossing of clock domains between high-speed serial I/O and slower parallel clock domains can now be accomplished with the dedicated logic included in the SerDes resources, which is of course in each IOB. When we couple these resources with the I/O clock resources, as well as the regional clock routing resources, this feature becomes very significant and well suited for source synchronous applications. We will discuss the clocking resources in the basic FPGA architecture memory and clocking resources module. The I/O SerDes capability includes input and output SerDes resources. There is an OSerDes parallel to serial converter for both OQ and TQ. It is arranged as a master and slave IOB pair to allow for differential inputs or larger single-ended bit widths. So not only can you complete 6-to-1 parallel and serial conversion, but when paired appropriately, you can do larger parallel and serial conversion. For this to be done, an appropriate master serial pair must be found on the die. You cannot just pair any two IOBs and make them a master-slave pair. The SerDes functionality also has a user-selectable fine-grained programmable delay element for synchronization. Each flip-flop has 3 control ports: clock, clock enable, and a set reset port. You have to remember that the clock enable and the set reset ports are active high. This is important when coding your HDL for the flip-flops. Likewise, note that there is not a separate set and reset port, just one port that is either set or reset. And this port can be asynchronous or synchronous. This is important because your synthesis tool should be able to map the set or reset to a LUT input if it is synchronous. This gives you more flexibility that is necessary for the tools to pack the most logic into the FPGA and get high speed, since all 8 flip-flops are required to share the same control signals. So our recommendations are to design for active high control signals and build with a synchronous set or reset. Besides building synchronously, you should also try to use the FPGA's global reset functionality whenever possible. This will allow you to perform a global reset on your system using a dedicated routing resource. This will require the instantiation of the startup component from the Xilinx Unified library that pertains to your chosen device family. Now this will save you from routing a high fan-out signal to all of your FPGA resources, which is a significant amount of routing. And don't forget to keep your control signals active high, so you don't need a local inverter to be mapped to each control signal input. These are not dedicated in the silicon, and that would force the synthesis tool to waste a LUT input. The reason we have spent some time discussing the limitations of control signals is that they can limit your ability to get high device utilization and high speed out of your FPGA. The reason this is necessary is the implementation tools can only pack related logic together in the same slice, since there are a limited number of inputs to each slice. This is important with registers since all of the flip-flops share the same control signals. Likewise, if the tools are going to use the 5-input LUT configuration, it has to be able to find another combinatorial function with 5 of the same inputs to be grouped into the same slice. You see, it's all about grouping related logic into the same slice. If the tools can pack related logic together, it does not end up wasting LUTs and registers. As I mentioned earlier, your synthesis tool can map clock enable and synchronous set or reset functionality to a LUT input. This is very powerful for being able to group registers into the same slice since all the flip-flops are required to share the same control signal. In this example, we see how a clock enable and a synchronous set or reset is mapped to a LUT input. Now this is very helpful, but a job only your synthesis tool can do. But if you build with an asynchronous set or reset, then it can't happen. In that case, the asynchronous set or reset would be forced to a register control port. Likewise, if you build with an active low control signal, the LUT will be required to invert the control signal. And as I mentioned, flip-flops with different control sets cannot be packed into the same slice. So in this example, we see 3 flip-flops are synthesized to force some control signals to be associated with LUT inputs so that these registers can be packed into the same slice. Now this is done in XST by using the reduced control set synthesis option. It is not done by default. Hopefully it will eventually, but what is most important is that you code for synchronous reset and code for clock enable so that you can take advantage of this functionality in your FPGA. That is, that your synthesis tool can take advantage of it. There are 3 ways to get the FPGA resources you need into your design. You can either infer logic with your synthesis tool, instantiate primitives from the Xilinx Unified Library, or instantiate an optimized component from the core generator. One of the biggest challenges for new users is to make certain that they are inferring the appropriate resources. First of all, one of the best ways to check that you are getting the resources inferred is to check the schematic viewer from your synthesis tool. All of the high-end synthesis tools have schematic viewers. The viewers are used to graphically display a gate-level version of your netlist and also a technology view of your netlist. While a gate-level netlist is worthwhile to check the Boolean optimization produced by your synthesis tool, the technology view helps you understand what Xilinx primitives were inferred by your synthesis tool or what primitives were not inferred by your synthesis tool. A primitive is a resource that is written to the netlist that represents a particular FPGA resource, such as a LUT, shift register LUT, or distributor RAM. Xilinx provides a library of primitives called the Xilinx Unified Library to all of our synthesis partners and customers so that they can create netlists that are optimal for their customer's design. Well, this same library is available to anyone who wants to instantiate a primitive into your FPGA. So if you're ever trying to work around what your synthesis tool won't do, you can always go here to the Xilinx Unified Library and instantiate the component. The core generator and the architecture wizards make larger optimized components available to you. While some cores have a charge associated with them, most do not. The cores range from simple components to large, highly complex IP. The architecture wizard is used most commonly to customize DCM and PLL components. All primary slice resources can be inferred by XST and Simplify. This includes LUTs, flip-flops, the shift register LUT, muxes, and carry logic. However, you must be sure to code for the resources properly. This means that if you define a flip-flop with an incompatible combination of control signals, you may get something slightly different, maybe a LUT input used for a control signal. Likewise, the shift register LUT is non-loadable, has no reset, and only supports a serial functionality. So if you code for a parallel read, you will get a pure register implementation, and this may not be what you expected. Similarly, muxes should use a case statement, and carry logic should use the proper arithmetic operator. Don't code for the XOR functionality and expect it to target the carry logic resource. In general, Inference is best and preferred by our customers. It assures portability to another technology and is, of course, reusable. However, most customers will have to do some instantiation of the design to get all the dedicated hardware they need. A list of Xilinx primitives and their behavior can be found from the library's guide for your chosen device family. This is available at support.xilinx.com or can be found from the Help menu from the ISE software. This will describe all the ports and attributes that can be customized. There is also a complete description of the XST attributes located from the software manual webpage. This is always a useful resource for inferring logic. The core generator and architecture wizards help you instantiate a high-level component. These cores are optimized and make designing for all the detailed functionality of things like the DCM or the PLL a lot easier. They also provide access to some very powerful design tools that can create common, sophisticated components at no additional charge. Now, before we wrap up, let's take one more short quiz to make sure you got the most out of this REL. In summary, all slices contain 4 6-input LUTs and 8 registers. LUTs can perform any combinatorial function of up to 6 inputs or 2 functions of 5 inputs. 4 of the 8 registers can be used as flip-flops or latches. The remaining 4 can only be used as flip-flops. Flip-flops have active high clock-enabled inputs and active high synchronous or asynchronous set reset inputs. Slice-L slices also contain carry logic and the dedicated multiplexers. The MUX-F7 MUX combines the LUT outputs to create 8-input multiplexers. The MUX-F8 MUXes combine the MUX-F7 outputs to create a 16-to-1 multiplexer. The carry logic can be used to implement fast arithmetic functions. The LUTs and the SLICEM slices can also create shift register LUTs and be used as distributed memory. And finally, manage your control set usage to reduce the size and increase the speed of your FPGA design. Well, there is lots of useful information about inference and synthesis attributes in the Synthesis and Simulation Design Guide. This is available to you from the ISE software using its help menu or directly from support.xilinx.com. The XST User Guide provides very helpful coding recommendations that all Xilinx users should live by. It also includes a detailed description about all of XST's synthesis options. This information can also be found from the help menu. If you would like to see what other courses we offer or what other free RELs are available, go to the Xilinx Education link you see here. I would also like to mention again that there are architecture modules available that discuss the basics of Xilinx's newest devices. You may find this useful, especially if you want to learn more about the device differences. But whatever you do, please take a second and let us know what you thought of this REL. Just click on the icon on the next page and tell us what you think. Again, my name is Frank Nelson. You've been listening to the Basic FPGA Architecture module for Virtex-6. Thanks for listening, and thanks for your business.